Our last kinetics topic to investigate is how does the rate of a reaction, or the rate constant, change with temperature, changing temperature. If we run a reaction and it gives this rate constant at that temperature, if you run it at a higher temperature, it gives a larger rate constant. One reason for this is you have more collisions. As the temperature increases, the number of collisions between molecules gets higher and higher. As you can see by this plot, it's an exponential increase. So this exponential increase is defined using, or is found using, the Arrhenius equation. That's this equation here on the chart. That says K as a function of temperature. It's not K multiplied by temperature, but K as a function of temperature is equal to A times E raised to the negative R, negative EA over RT. That's activation energy. That EA is activation energy. R is our standard R that we're familiar with, 8.314 joules per mole Kelvin, and temperature must be in Kelvin in order to cancel out. That A term is called the collision frequency, the frequency factor. That thing is different for different reactions. That term is different for different reactions, but it can be considered constant over a pretty large temperature range for a specific reaction. So collisions are obviously, the number of collisions are obviously a factor in determining how the rate changes as a function of temperature, but that's not the only thing to consider. As you increase the temperature, the number of collisions increases. That's why the rate gets faster. But additionally, as the temperature increases, all of the molecules in that reaction have more kinetic energy, or there's greater spread of kinetic energy. So if we look at this plot on the right, this can be considered the plot for a cool gas, we would say. That activation energy barrier is there, and everything in pink shaded underneath that curve, that's the number of molecules that have enough energy to get over the activation barrier. Remember, the activation barrier is this hump down here that reactants have to go over that hump to get down to products on the other side. If you heat that reaction, we'll say it's a gas, but if you heat that reaction, the whole curve spreads out, and you have a greater spread of kinetic energies of your molecules. And there are many more molecules shaded under the pink area of that curve. So there are many more molecules that have enough energy to get over the activation barrier. So the number of collisions and the activation energy are the two major things that tell you how temperature affects rate constant. So this Arrhenius equation is an exponential equation. But at this level of chemistry, we don't often work with exponentials. We work with linear things. So let's see if we can get this into a different format to make it a linear relationship. The first thing we do to make it a linear relationship is take the natural log of both sides. So ln of k equals ln of a plus negative EA over RT. The natural log made the E cancel out. Then if I just rearrange it, all I did there was rearrange it, pull the EA term out front. The reason I want to rearrange it is so that I can have it in the y equals mx plus b linear form, point slope form. Nope, I say it wrong every time. Slope intercept form. So I can plot ln of k on the y-axis and 1 over t on the x-axis, and I will get a graph that has a slope of negative EA over R, and I can figure out my collision factor, my frequency factor, from the y-intercept. So if we look at a plot of the same data, remember, as 1 over t, as temperature gets bigger, 1 over t gets smaller, so that's why these points are going backwards as the temperature gets hotter, but the ln of k increases. As temperature increases, k increases. But the reason we plotted ln of k versus 1 over t is so that we can have a line like this, where the slope of that line is negative EA over R. So you can figure out your activation energy from that line, and you can figure out your collision frequency factor from that line. Yep, good news. You may also see the Arrhenius equation written in this point slope form. Yeah, all three of these equations are Arrhenius equations. It's just the exponential form the slope-intercept form, and the point-slope form. It all tells you the same type of things. You just use different equations based on what data you've been given. So you're going to do this activity as part of your assignment for today. Question 2 and 3 asks about a reaction Q going to products and a reaction W going to products. It says Q has a higher activation energy. So I have drawn these two plots to keep in mind, to have a picture in your mind of higher activation energy means bigger hill over here. Remember, the bigger the hill, the slower the reaction, because reactants have to climb that really tall hill to get to products on the other side. So bigger hill, slower reaction. Bigger activation energy, slower reaction. Slower reaction, smaller rate constant. I think that's good enough for this one. That's all with kinetics.